Hi, everybody. Welcome to Math with ACE. We are continuing our exploration into statistics. We have been dealing with inference lately. We worked on confidence intervals, and then we moved on to hypothesis testing, where we were testing claims about a single population, dealing with either averages or percents, which we know them as means and proportions. But now we're going to take that knowledge and we're going to go a little bit further and say, what if we want to compare groups? What if we want to look at maybe the average pass rate at Solano College versus Napa Valley College? What if I wanted to know the proportion of people who buy red cars in Texas versus Louisiana? So I'm comparing two groups here. And so I have two things that I need to consider. And that means that when we check our conditions and we calculate our test statistic, things are a little bit different. Now, remember, when we are running the hypothesis testing, we do our statement where we identify our hypotheses and we identify our parameters and context as well as our level of significance. And then the next thing that we do is we check conditions. And when we check conditions, we are going to be checking the same conditions for this hypothesis testing. Everything should feel very similar. The only difference is that we are checking conditions for both sets that we're working with. We are dealing with were both of the samples randomly selected. Let's recall that for hypotheses, your null hypothesis is always a statement of equality. So we have this equality that we need to consider. And your alternative hypothesis is always the claim that you're testing. And the way that we test our claim is we're either saying that one group is less than the other, one group is more than the other, or one group is different than the other. Okay, so it's not necessarily in our equality statement, you know, that some books will say less than or equal to, greater than or equal to. We're not doing that. We are assuming an equal value, and then we're testing less, greater, or not equal. When we were dealing with proportions, we had that the parameter was equal to some hypothesized value, and then the parameter was either less, greater, or not equal to that hypothesized value. And it looked something like this. And we had either less than, greater than, or not equal to, and that hypothesized value was the percentage from the claim. So for instance, 25% of the population did this, or more than 30, or something like that, where P sub 0 was a hypothesized number. The same thing was true for means. Means looked like mu equal to that hypothesized value. And the alternative was mu is less than, or mu was greater than, or mu was not equal to. And that was a hypothesized value as well. So for instance, I think the average age of people who buy Labubus was 12 years old, or I think it's less than 12 years old, or I think it's different than 12 years old, or something like that. Now, when we're talking about two groups, we have P1 and P2, mu1 and mu2, or you can use different subscript. But our hypothesis looks a little bit different to where you are now considering two separate groups. And we initially assume that they're equal. Now, I want to show you that if I was to have this statement and I wanted to move a variable over to the other side, I wanted to undo what it is to inverse the operation so that I can get it to the other side, I would subtract it from both sides. And so I would have P1 minus P2 equals, and P2 minus P2 is 0. This is an alternative to what we have originally. You can either write P1 equals P2, or you can say P1 minus P2 equals 0, meaning there is no difference. Both of these are acceptable notation. So it would be in your best interest to be familiar with both of them. The alternative is then the same thing, but we use those symbols. less than, greater than, and not equal to. So we could say that the first proportion of the population is less than the second, or the first proportion is greater than the second, or the first proportion is different than the second. And then again, in that same notation, subtracting over, I could also write these as that subtraction with those same symbols, less than, greater than, or not equal to, and 0. And typically we're talking about whether there's a difference or not. And if there's a difference, that means that when you subtract the two, the value is not 0. So I get $10, you get 20. Do we have the same? No, it's different. 20 minus 10 is 10, which is not 0. If we had the same 10 and 10, when you subtract, 10 minus 10 is 0. So difference really works with 0. You could do a hypothesis test where they're giving you a value that's not 0, but that would need to be stated in the claim. We're wondering if the difference is more than 5 or more than 10% or something like that. But most often it's going to be equal to 0 and using 0 as our value. Now, it's important that you establish what P1 and P2 are. So P1 is the true population proportion of students who pass at Napa Valley College. Students who pass their math class on their first try at Napa Valley College. And then P2 would be the same thing, except at, let's say, Solano College. Okay, so you would want to write out the whole thing. There is another notation that we could use where instead of 1 and 2, we could say PN and PS, where N stands for Napa Valley College and S stands for Solano. That helps you keep things in order. It's very important that you are paying attention because when you're doing a less than or a greater than, the order in which you put your parameters matters, and you have to follow that through all the way for your statistic. So the same notation is true for means. Mu1 equals mu2, mu1 less than, greater than, not equal to. So we could say originally mu1 equals mu2 or mu1 minus mu2 equals 0. And then the alternative are the symbols that we've been dealing with, less than, greater than, or not equal to. And then we could also do the subtraction. I'm not going to mandate which one you use. It's whatever you feel comfortable with, but you will see it if you're using different calculators, you will see different notation. So it's important to be familiar. And then you have to identify what's 1 and 2. That's how we set up our hypotheses. When we're checking our conditions, you have to check for both. Okay? Checking conditions. Random for both groups. So a lot of the time we're saying a sample was random as stated. Sample is singular. You would need to say samples are random as stated. Otherwise, you're implying that you're only checking one. So the English and the way that you write this is important. Independent, both groups must be checked. And remember, we randomize, or we make sure that they're random in order to eliminate bias and to create groups that are similar to the population so that we can generalize to the population. So typically for random, this is typically stated in the problem. For independent, remember you're multiplying the sample size by 10 and making sure that the population is larger than that. So you would need to say N1 times 10 has to be less than or equal to N1, which is large population, And also N2 times 10 has to be less than or equal to large N2, where N1 is the first sample size and N1 is the first population size. And N2 is the second sample size. A lot of times they're not going to tell you which one is which. You decide and follow through, and your calculations will work out the same. If you did one is the other, like one will be positive, your test statistic will be positive, one will be negative, test statistic will be negative, and the follow through works out for the same for both of them. And then N2 is the second population size. Okay. So far, so good. A lot when you're checking the independence, remember you are typically like we're assuming that the population, this is from a large school, we're assuming there's this many people. A lot of times you're not given what the population size is, and you're making an assessment. That's fine. Large counts. For proportions, there's one way. You check successes and failures. For means, there's three ways. You check either the population stated to be normal, which rarely happens. It's only in like a perfect world. The sample size is large enough, or you have to graph it and your graphs don't show skewness or outliers. When we were doing confidence intervals for proportions, we used the sample proportion to check the successes and failures. When we did hypothesis testing, we used the null hypotheses to check, or the null and the alternative hypotheses values to check the expected successes and failures. Well, now when we're comparing two groups, we need to go back to using these sample successes and failures. So that's going to look like, for proportions, N1 and P hat 1 have to be at least 10. N1 and 1 minus P hat 1 have to be at least 10. N2 and P hat 2 have to be at least 10. And N2, 1 minus P hat 2 have to be at least 10. These are successes and failures for the two samples. For means, you need both populations to be given as normal. Or both populations are, or both samples are at least 30 by the central limit theorem. Or both graphs of the box plots and histograms show no outliers or skewness for both samples. Okay. Now we need to know how to calculate the test statistic. When you are calculating the p-value, you're using the same approach. You're looking at your alternative hypotheses to tell you whether you are going to be doing a less than, a greater than, or a different than test for either t-distributions or normal distributions. And a lot of times you want to be looking at actually using, we're going to use Staplet, but actually performing the calculations in one categorical for multiple groups or one numerical for multiple groups. So it just depends on the way that we're doing it. I'm going to show you what the test statistic is, and then when I go through the examples, I'm going to show you how to use the calculations, but also I've given you those instructions in the book. All right. As always, for proportions, we are doing a Z test statistic. We're calculating a z-score. For means, we are doing a t-test statistic because only in a perfect imaginary world are you going to be given the population standard deviations. And so because of that, we're never using a z-test statistic. So if you're using ChatGPT and it's telling you to use a z-score, not a good idea. So before, for one sample, we had z equals p hat minus the hypothesized value divided by the square root of the hypothesized value 1 minus the hypothesized value over the sample size. Now, we're not using that same standard deviation because we don't have an assumed population value. We're talking about a difference here. So the way that we expand this for two samples is first we want to pool our proportions to calculate a pooled, because we're assuming that they're the same. So we are going to pool our proportions together, and we're going to write P sub C to pool together. And what you do is you take your successes together and your sample sizes together, and that is your pooled proportion. So we're going to call this PC, which is like combined, where you take the successes of sample 1 plus the successes of sample 2, and you divide that by the sample size of sample 1 and the sample size of sample 2, and that is your new pooled proportion. We are assuming that the proportions are the same. That's what we're testing, so we want to combine that. So instead of using P sub 0, we're going to be using P sub Z, but we have two sample sizes. So our z-test statistic is found by looking at the difference of sample 1 minus sample 2's proportions minus the hypothesized value, which again, this is most often 0. That comes from your alternative. If they're equal to each other, then it's 0. If there's a number, it's different. But then in the denominator, we're using PC, 1 minus PC, so that proportion, and then its complement, times 1 over the first sample size plus 1 over the second sample size. You don't need to memorize this formula. Remember, you're allowed to have your notes to help guide you, but it's important that you understand what the pieces are. You first have to pool your proportions together, successes added, sample size added, and then you divide. Order of operations is very important. And then you have two sample sizes, so you need 1 over N1 and 1 over N2. And then you have your differences. This is your Z statistic. Let's go do the same for means. For means originally, we had a t-score equal to the statistic x bar minus the hypothesized value of mu, but we did not know the standard deviation, so we used standard error here of the sampling distribution. And how we found that was by taking the standard deviation of the sample and dividing that by the square root of the sample size. Okay, so let's look at what happens when we are doing two samples. We don't have a combined proportion here, or we don't have a combined value like we did for proportions, but we have a t-score, and we're doing the difference of the statistics as with proportions, and the difference of the hypothesized values as with proportions. And again, this is most often 0. But then in the denominator, instead of having sample size over root n, we need to do it twice. And the way that this looks is we're going to square root, but we're going to put the square root over the entire denominator, which means we need to square the sample size. So if I was to take this square root and actually do it over the entire thing, I need to square the standard deviation to counterbalance square rooting. So to undo the square rooting of the entire thing, I square it. So what you would see here in this two samples is the standard deviation of the first sample squared divided by the first sample size, and then the standard deviation of the second sample squared divided by the second sample size. Okay. We are going to be calculating these by hand. We're also going to use calculators to help us. But this is the broad strokes overview of what happens when you go from one sample to two when you're hypothesis testing for both means and proportions. Stick around for our example video so you can see how this all comes together.